Yeah, we shouldn't get carried away chatting. Like, okay, yeah, sorry, I got a little bit carried away chatting. We have a tight schedule. So it's a great pleasure to announce our very first speaker, Oscar Randal-Williams, who is a professor in Cambridge. And let me say a couple words about Oscar. So Oscar graduated in 2009, I think, in Oxford with Ulrike Tillmann. He's a topologist, and then he's most well known for his amazing body of work together with Søren Galasius, and also his recent breakthrough work about diffeomorphisms of disks. Oscar got a bunch of prizes. I guess let me mention a few: the Whitehead Prize, I guess recently the Clay Research Award together with Søren, and the Oberwolfach Prize. And he also gave a talk on the last ICM. And today he's going to talk about the cohomology of moduli spaces.
Okay, thank you very much for the introduction and for inviting me to speak here. So I want to begin by doing a little bit of propaganda for my subject, and then I want to tell you about a case study, which is a recent result in this sort of area that I've been a little bit involved in, but was mainly been done by other people. So moduli spaces mean spaces of mathematical objects of some kind. And the most famous one is the original one due to Riemann, MG, so the space of genus G Riemann surfaces, where moving in this space means deforming the complex structure a little bit on the Riemann surface. But there's many other ones as well. So you can imagine a space of metric graphs, maybe of a fixed topological type, maybe having G loops, and deforming in this space means deforming the lengths of edges, deforming the metric. You can imagine, maybe we'll skip the third one, but you can imagine the space of n points in a plane or in some space, and moving in this space means the points move around, but maybe they never collide with each other. The one that I've mainly thought about during my career is the last one, the space of submanifolds of R infinity of a fixed topological type. And all of these are somehow moduli spaces. As soon as I tell you the space, we agree that this is some kind of moduli space of some kind of mathematical object. And if a moduli space M classifies some kind of object X, then the cohomology of this moduli space is exactly just invariance of families of this kind of mathematical object. So more precisely, the Deith cohomology with coefficients in some abelian group A is just the A-valued invariance of D-parameter families of whatever we're studying. So this generalizes invariance of the objects themselves. So a zeroth cohomology class is just a deformation invariant number of objects in question. And so, for example, in the original definition of moduli space, the moduli space of Riemann surfaces, it's a theorem of Klein from 1882 that this space is connected. So in other words, any two genus G Riemann surfaces you can get from one to the other by doing a deformation of the complex structure. So when I phrase that in terms of cohomology, that's saying that the zeroth cohomology is Z. If you go up a little bit, it's a theorem of Mumford from the 60s that the first cohomology of MG turns out to be 0. So in other words, there's no invariance of one parameter families of Riemann surfaces. There's no integer valued invariance at least. And then it's a theorem of Hare from the 80s that the second cohomology, so there's one invariant of two parameter families with values in integers. It's the so-called Hodge bundle. I just sort of want to point out that this is over the course of 100 years that these three calculations were done. Now we know a lot more about higher dimensions as well, but it was a bit slow to get started, perhaps. And so many kinds of mathematicians are interested in modular spaces. So you may be coming from algebraic geometry originally, but also from mathematical physics, from number theory, from straight topology like myself. And especially with examples like modular space of Riemann surfaces, all of these communities are interested in them, which makes them particularly rich places to work somehow, because there's many different perspectives on how to think about them. But over the last 25 years, there's a new community that's emerged that are thinking about modular spaces, of which I am a member. And this comes not from any of those subjects mentioned before, but basically from homotopy theory. And the beginning of this was the work of my PhD advisor, Ulrike Tillmann, who related Riemann's modular space to so-called infinite loop spaces, which is a classical topic in homotopy theory that's been studied since the 70s, but is not the usual thing that people who think about MG had ever thought about. And the breakthrough result in this subject about 20 years ago was by Ibn Mazdin and Michael Weiss, who's in the audience somewhere, which was a calculation of the cohomology of MG completely in a range that diverges with G. And these days we know the range is exactly 2G minus 2 over 3. So that means if G is very large, then we know a tremendous amount of the cohomology of these modular spaces. So this new community has a kind of different toolbox to the tools that are used by algebraic geometers or what have you. These are somehow based on ideas in homotopy theory, in particular Quillen's ideas about the foundations of algebraic K-theory. And because it's a different and relatively recent box of tools, it's able to solve problems that maybe seem difficult if you don't know these kind of tools. So when they applied, these methods have led to very significant results. So today I want to, instead of trying to explain something about this field to you in general, which would be a little bit hopeless, I just want to talk about a recent example. I've called it a case study, where these kinds of methods are used to prove what I think is a quite important theorem. So to get started, this is the modular space we're going to be interested in. It's something incredibly classical. It's the modular space of n particles in the plane. And these are somehow n indistinguishable particles in the plane. So to make a literal definition, I take tuples, n tuples of points in the complex numbers, which are all different, but then I divide out by the symmetric group action, which reorders them. So these are indistinguishable particles in the plane. And so because they're indistinguishable, we may as well record them by recording the unique polynomial monic, which vanishes at those points. So we can think of n particles in the plane as being exactly the same data as a degree n monic polynomial of the complex numbers. So there's a picture of some number of points in the plane. And this space has been well known in topology, of course, for a long time. Maybe it's most famous in connection with the braid group. So the fundamental group of this space, the space of loops in this space, well, a loop in this space is exactly a so-called braid, meaning a picture like on the right-hand side. So some strings that you braid together, and they go from the top to the bottom. And if I have two such pictures, I can stack them on top of one another, and those form a group. The so-called Artin's braid group on n strands. You can make the number of strands be whatever you like. And it turns out that these spaces are what we call in algebraic topology Eilenberg-MacLane spaces, which means that everything about them is encoded by their fundamental. So studying these spaces is, from any point of view you like, identical with studying the braid group. But sometimes it's convenient to think group theoretically and think about the braid group, and sometimes it's convenient to not think group theoretically and think about the space itself. And in particular, by not thinking group theoretically, Arnold calculated completely the cohomology of this space. And the answer is quite surprisingly simple. I've written it with rational coefficients. And what happens is the following. It's one-dimensional in degree 0. It's one-dimensional in degree 1. And that's it. So there's only one invariant of n points in the plane, which is the number of points in the plane, n. And there's also only one invariant of one-parameter families of points in the plane. And that is something like a total winding number of this picture. You can't quite measure winding numbers because the points are indistinguishable. So you can't measure how much the ith one winds around the jth one because there is no I and j. But you can, in a sensible way, measure how much the points wind around each other in a picture like this. It's represented by a completely explicit differential form on this space. And it's kind of incredible that the answer is so simple. And it's also kind of incredible that the answer, as long as you've got at least 2 points, doesn't care how many points you have. It doesn't get more complicated the more points you have, nor does it get simpler. So here's a construction one can do if I give you n points in the plane, or in other words, if I give you a monic polynomial of degree n, you can make the branch cover of the plane, which is branched exactly at those points. So that means you write down the following Riemann surface, you write down pairs x comma y, where y squared is d of x, and d is your polynomial that you chose to begin with. So that is just an explicit construction of the double cover of the complex plane, which is branched exactly at those points, and is branched at those points, not just maybe branched at those points. This is a surface, right? I have 2 complex variables, and I've set one complex equation between them, so the thing is one complex dimensional. It's a topological surface. And it turns out that depending on the parity of n, it either has one or two boundaries, and its genus is either n-1/2 or n-2/2, whichever one is an integer. If I take, this is just a picture, it's very difficult to draw branch covers, or at least I found it very difficult. If I take the branch cover of the plane branched at 2 points, you can think about it as taking two planes, cutting the arc between them open on the two planes, and then gluing them together in the strange way. So the back arc on the top plane glues to the front arc on the bottom plane, and so on. So this, you can't draw this embedded into three-dimensional space, and so it's very difficult to think about. But that's just a picture of the branch cover with 2 points. And as you see, well, you can't quite see, but you can see that it has two boundaries, sort of two ways to escape to infinity. And you can't really see that it has genus 0, but it does have genus 0 if you think about it. So this is the construction you can do with some points in the plane. You take the double branch cover over those points. And now that's a topological surface, and we can look at its cohomology. So in other words, we can look at for example, the harmonic one forms on this surface. That's a finite dimensional vector space of dimension approximately g, or dimension approximately n/2. And it turns out that it has, because of so-called Poincare duality, it has a symplectic form on it. That's not so important for what I want to say. So this is saying that for every polynomial, I've given you I said integer coefficients, but I could well have said rational. Let's just say, imagine I did say rational. I've given you a vector space with a symplectic form on it. And as I deform the points in the plane, that vector space changes. It becomes the first cohomology of a different surface as I vary d. But it changes in a continuous sort of way. This is the so-called Burow representation of the braid groups. So remember, a braid was a loop in this space. So if I pick a vector in this vector space and transport it around a loop, it comes back probably to a different vector. And that's a representation. It's called the reduced integral Burow representation. So that's somehow the group theoretic way to see it. It's a representation of the fundamental group. The geometric way to see it is that it's a local system of abelian groups on this configuration space. So because of this case distinction, depending on the parity of points, let me always suppose from now on that n is odd. And let me write it as 2g plus 1, and then the branch cover has genus g. Okay, so I'll refer to g, the genus of the branch cover. And in this case, the reduced integral Burow representation maps from the 2g plus first braid group to the symplectic matrices of size 2g. And this can all be made completely explicit. So the braid group has a completely explicit presentation found by Artin. The symplectic group, we of course know, is matrices that preserve a symplectic form, and you can write down where all the generators go in a completely explicit fashion. Okay? For the kind of questions that I'm interested in, that's of no use whatsoever. Making the representation, like writing down the matrices for it, is not a helpful thing to do for the kind of questions that I'm interested in. But it's maybe reassuring to know that it can be done. So the sort of questions that you can ask now, given this setting, is a sort of version of invariance of families. But now I've put this V, so this Burow representation, as the coefficient. So what that means is I'm looking for invariance of, let's say, configurations of points that take values in an abelian group, which depends on where the points are. So not in a fixed abelian group, but over each configuration, the invariant takes values in some abelian group that's allowed to vary with the configuration. But it varies in a precise and predetermined way. Okay, so I've fixed the representation V, the fundamental representation of the symplectic group, and I'm looking for invariance of families of configurations that take values in an abelian group that transforms in a fixed way. And once you've got this far, there's no harm in generalizing a little further. So the symplectic group has many representations, not just its fundamental representation. And you may as well ask the question with all these other representations. So it turns out the algebraic representation to the symplectic group, they're called V sub lambda, where lambda is a partition of some number into at most G parts. So the representation to the symplectic group, the algebraic representations are completely classified, and they just all have that sort of way of parameterizing them. So this is a question you can ask. And I want to come back later to answering this question, or not really to answering it, but to saying something about it. But I first want to do something else, which is explain why you would like to answer this question. So for somebody like me, I think this is a very natural modular space. This is a very natural family of coefficient systems over it. I like calculating things and getting an answer, so it seems like a quite tempting kind of calculation to do. But this very particular question has, in some sense, much better motivation than, well, it's nice to calculate things, coming from arithmetic statistics. So, so this will have a bit of a different flavor, but hopefully there will be an analogy that's somehow visible. So I want to fix an odd prime power q, and I want to look at, again, monic polynomials with no repeated roots. You have to interpret repeated roots as meaning over any field, not just maybe over fq. And let me say of odd degree again, degree 2g plus 1. Then we can write down the exact formula that I wrote down before. I look at pairs x, y, such that y squared is d of x. But now we're not thinking of x and y as being complex numbers. We're thinking of x and y as being elements, if you like, in the field fq, or maybe elements in any field that contains fq. Because as long as the polynomial d makes sense over any field that contains fq, and so we can look at solutions there. So in algebraic geometry, that's what's called something like a scheme, meaning that we haven't quite predetermined where we're looking for solutions. We're just looking for solutions over any ring. And again, this is sort of the same formula. I've even used the same letter for it. This is a curve in the sense of algebraic geometry, meaning it's one-dimensional in some sense. But it's a very different flavor. Before we had a Riemann surface, and it was a topological space, and we could think about its topology. Now, at best, this is something like a set of points, or a set of points for every ring for which we ask the question, what are the solutions to this polynomial? And so we can ask that question. And instead of asking what are the solutions, we can ask a maybe more naive question, which is how many solutions are there to this polynomial? Let's not try to find them. If over fq, of course, there's at most q squared, because even before we impose an equation, there's at most q squared pairs of points. And so then we put an equation and there's probably less. It turns out that the wise thing to do is not to ask exactly how many solutions are there over fq, but to ask that for every extension of fq. And that can be arranged in the following thing. I apologize for the size of the formula. I'll try to speak through it. So let me explain somehow from left to right. So we look at how many solutions there are to this equation over fq to the k, meaning over some extension of fq. And there'll be a finite number for every extension that we take, and so we count them. We assemble those into this sort of logarithmic generating function, and then we take the exponential of that. Forget about the right-hand side for now. Okay, the left-hand side has some radius of convergence. That's 1 over q, it turns out. And then it's not at all obvious, but it's true that that's equal to a rational function. This is known as the L function attached to this curve, CD. And the denominators are known. I mean, they're 1 minus t and 1 minus qt. And the numerator is some polynomial with integer coefficients. Okay? This is, as I said, called the L function attached to this situation. It's meant to be analogous to the Riemann zeta function. In particular, it has all sorts of properties like a functional equation and so on. And it has, just like the Riemann zeta function, it has a critical line. That would be real part 1/2 for the Riemann zeta function. It turns out in this situation, it's t equals q to the minus 1 over 2 is the critical value. And then people who think about these kind of things are interested in sort of what can these polynomials be that you get by picking, you know, if I pick a different polynomial d, I'll get a different answer. But like, how different can it be as I go varying d? And there's a conjecture about this kind of thing. It's a conjecture due to Conrey, Farmer, Keating, Rubinstein, and Snaith. And let me talk you through this as well. It says we look at these values, PCD, at the critical value, which is q to the minus 1/2. We're interested in not just the averages of these things, but their moments. So in other words, sum of their rth powers for some fixed r. And then we renormalize by some constant. And there's a specific conjecture which says that this left-hand quantity, as we average over all monic square-free polynomials, of which there's finitely many, of course, is a specific polynomial, QR, applied to the number 2g plus 1, plus an error term that's little o of 1 in g. And this QR is an explicit polynomial that's known, but which I won't try to communicate to you. Let me just say its degree is r times r plus 1/2. So there's a little star here because this was not really their conjecture. Their conjecture was something about number fields. But in this kind of business, whenever you have a reasonable statement about number fields, you can ask the analogous thing for so-called function fields. And so what I've written here is the somehow function field version of what they actually conjectured. So what this is saying, this is an estimate for rth moments of these central values of the L function as in the large G limit. And it's saying something about how, to some leading order, it looks like this specific polynomial in 2G plus 1, and then the error term is little o of 1. So this slide is completely about counting and arithmetic. The previous slides were about topological spaces and making Riemann surfaces by taking branch covers and so on. It turns out there's an incredible relationship between arithmetic and topology that can be used so that somebody who knows about topology can actually prove statements that sound like, which are in arithmetic. So this, roughly speaking, relates the following two kinds of quantities. On the arithmetic side, it is to do with counts of how many solutions over various fields a given system of equations has. Here, what I've called a scheme. You just think about it as a system of polynomial equations. And on the right-hand side, it has to do with the ordinary topologist cohomology of the complex points of that system of equations, which you just think of as a topological space and has nothing to do with arithmetic anymore. So that's the version without brackets, and the version with brackets is that you can do weighted point counts on the right-hand side if you're happy to do cohomology with local systems of coefficients on the topological side. So this is an enormous and non-obvious edifice that's built on all sorts of parts of the algebraic geometry of the 60s and 70s. It uses the so-called Grothendieck-Lefschetz trace formula. It uses Artin's comparison theorem to relate so-called étale cohomology with topologist cohomology. And then it uses so-called Deligne's bound on Frobenius eigenvalues to get rid of something that would otherwise be incomprehensible. Let me give you an example of what this might look like. So an example of the first step is, roughly speaking, the following. The number of solutions over FQ of some system of equations is given by some regularization times the alternating sum of the trace of some maps called Frobenius on the étale cohomology of the object that you're looking at. So that's basically what I've called the Grothendieck-Lefschetz trace formula. The thing called the comparison theorem is that on this equation, you can swap under good conditions these étale cohomology groups, or homology, I suppose I've written it here, for ordinary topological homology of the complex points. Under good conditions, for example, if X is proper, but also under more general conditions. And the third thing is that writes it as an alternating sum of some maps that you know nothing about on some cohomology groups that maybe you do know something about. But Deligne has proved that the eigenvalues of these Frobenius maps are bounded in a certain way. And so just by knowing the dimension of the vector space, you can estimate something about the traces of these maps if you have an a priori bound on the eigenvalues. So that's somehow the strategy. And let me give you an application of this. Imagine we apply it to this example that I talked about of endpoints in the plane. If we think about endpoints in the plane over finite fields, that's exactly counting how many degree n polynomials there are with no repeated roots, if you set things up correctly. And we can input this calculation due to our null that I told you, that the cohomology of configuration space is very simple. It's Q in degrees 0 and 1 and nothing otherwise. And if you input that in this kind of formula and go through the motions, you discover that you get exactly Q to the n times 1 minus Q inverse. In other words, maybe it's more natural, instead of counting how many polynomials there are with no repeated roots, we think about the density of polynomials with no repeated roots. So that means we divide by Q to the n. And then it's saying that the density of polynomials with no repeated roots is exactly 1 minus Q inverse. And that, I'm sure, one can prove by doing number theory, but one can prove by doing this topological calculation and going back and forth through this machinery. So this is a sort of surely a toy example of this trick, but it's an example of it. So the the work I want to tell you about, which is new, begins with work of Jonas Bergström, Adrian Diaconu, Dan Petersen, and Craig Westerland, where they decide to approach this conjecture of Conrey, Farmer, Keating, Rubinstein, and Snaith using this strategy. You have to apply it to, roughly speaking, this configuration. You do a small amount of violence to it, but it's basically this configuration space example. You use a local system, which turns out to be, you take this fundamental representation V, you take its exterior algebra, so all exterior powers, and then if you're interested in rth moments, you take the rth tensor power of that. It turns out that's the correct local system to use. And if you do that, then the weighted point count is exactly the left-hand side of this conjecture. And that's not, I mean, that's because you've chosen the local system to make that be true. So that somehow puts the left-hand side of this conjecture into this framework. And then what they do is two things. Firstly, this is some representation of the symplectic group, and you can use classical representation theory to explain how to build it in terms of the representations whose names you know, the ones called V lambda. It turns out the multiplicity of each V lambda is a certain number that's a given polynomial in 2g plus 1 of degree exactly what this conjecture of CK FRS tells you. And then they do two things. They completely calculate what you get in the large genus limit for these cohomology groups with heuristic coefficients. And they show that when you combine that calculation with these explicit polynomials P lambda R, you exactly get what the right-hand side of this conjecture predicts. These polynomials I called capital Q R of 2g plus 1. So I won't give you the answer for this. It's not complicated, but it involves notation and some yoga of symmetric functions and stuff. But let me just say there's a explicit answer from which you can extract any kind of thing you might want to know. But that is about the G goes to infinity actual limit. It's not about what happens for big G. It's about literally taking the limit. And the second thing they do is they explain that the conjecture of CFKOS would follow if one knew the following thing. If one knew that for fixed R and all big enough Q, the cohomology of these spaces, of these configuration spaces with these V lambda coefficients, didn't actually depend on G. And more precisely, there was a range that was linear in G. Okay, and they show that, so they do the first thing and they explain that if the second thing were true, then this conjecture would follow for big enough Q. So let me say something about how they do this. So the strategy they use is, in some sense, the kind of thing that is by now standard in this kind of homotopical approach to computing cohomology of modular spaces. The key thing that makes this whole homotopical approach work is that many of these modular spaces that I wrote down on my very first slide are in some sense local in whatever background space things are living in. In particular, if I have a subset of the complex numbers and I want to check if it is indeed a configuration of finitely many points, I can check that locally in some sense by checking that locally it looks like a discrete set and by checking that the whole thing is bounded. And more precisely, the construction that assigns to an open set the set of all discrete subsets of U is what's called a sheaf on the complex numbers, and it's almost what's called a homotopy sheaf. And if I take the so-called compactly supported global sections, I get all the configuration spaces at once. And this sort of local to global principle, so the global thing is what we're interested in, and the local thing, it comes from assembling local contributions in some way. That somehow is what makes these homotopical methods work. Of course, there's still things to do, but that's a key feature of it. Now, this is all well and good for computing ordinary cohomology of things, but something like V lambda is a local system on the configuration space by definition, but it's not in any meaningful sense local on the complex numbers. If I want to know the value of this V lambda, I need to know where all the points in the configuration are so that I can make the branch cover so that I can take its cohomology. And that answer cannot be communicated as some kind of local contribution from each of the points in the configuration. It depends where they all are simultaneously. It cannot be expressed in some sort of local terms. So that's somehow a difficulty. And to get around that, they use a strategy that I introduced a few years ago for a different example, which is that there's a different thing you can do, which is more manifestly local. So you can make the following space. You can look at, I've decorated it with an X. So I look at pairs of a configuration and an X-valued function on the branch cover that you make out of that configuration. And giving a function is the canonical example of something that's very local. To give a function, you have to say what it is locally, and then you have to check that your two choices that you've made locally agree whenever you've defined it twice for some reason. So this somehow is describable locally on the complex numbers. And the sort of, roughly speaking, standard methods that we know by now apply perfectly well here. What you can do is you can make the following, I mean, there's different ways to say it. You can make the following observation. Once you've computed the answer for this, whatever you've done, you can treat this X, roughly speaking, as a variable. You never have to pick a specific actual space to take maps to. You can consider this as some construction that's functorial in the space X. And you can consider the answer you get as something that's functorial in the space X as well. And then you can identify, as it were, those two functors without ever having to pick a specific space X to identify. And if you do this, it turns out this lets you calculate the cohomology of configuration spaces with loads of local systems. And what's left is a problem in classical representation theory, which is to make sure that every local system you were interested in shows up somewhere in this massive mess, and that you can pick out the bit that you were interested in from the massive mess. But that somehow is, I mean, of course, you have to do calculations, and how good you are at doing the calculations depends on whether you get the correct answer or not, but it somehow is a more or less routine thing to actually do. So the strategy is to somehow change this not quite local question to a different, obviously local question, answer that, and then use that you produce so many examples of twisted cohomology calculations that the one you are actually interested in must be in there somewhere. And then you go and look for it. So as I said, they reduced this conjecture to the following kind of question, which is to know that the cohomology of these configuration spaces with various local systems are independent of G in a range that's sort of linear in G. Okay? This is a kind of theorem that is not unheard of. There's an entire industry called homological stability, which is all about proving theorems that have this kind of flavor. You've got some sequence of spaces, and you're asking, is it true that a given cohomology group stops changing if I go far enough along the sequence? And this is, here the sequence is clear, it's parameterized by G, and it's a little bit fancy in the sense that they have local coefficient systems on them as well. But apart from that, it somehow fits very well within that paradigm. And if one is just interested in some kind of range, it fits so well in that we just know it. So it follows, there's a machinery for studying this kind of homological stability questions. A few years ago, Natalie Wahl and I wrote a kind of formalization of this machinery, and this example fits into that machinery. But what it gives you is a range that looks as follows. It's I less than G minus 1 plus the size of the partition lambda over 2. And that is useless for this question. For this question, it's essential that the range you get does not care about lambda, because you're not really going to apply it to V lambda. You're going to apply it to this Rth tensor power of the exterior algebra of V. And roughly speaking, all V lambdas show up in that. And here, if all V lambdas show up, in particular ones where lambda is approximately 2G will show up. And then this range is approximately negligible. So it's completely essential for this application that you have a range that does not care which representation you're putting in. And that is not something standard in this kind of business. The kind of results one knows in homological stability with coefficients are always of the form that it improves with the parameter and it deproves with the so-called polynomiality of the coefficient system, which here means what is lambda a partition of. So what we do is show that nonetheless it's true. You have to have a slightly eccentric coefficient, which is 1/6. But this kind of stability range is true in degrees less than 1/6 times g minus 1. And if you combine that, so this is what I should have said, this is work of myself, Jeremy Miller, Peter Patzt, and Dan Petersen. If you combine this with the previous work of Bergström, Diaconu, Petersen, and Westerland, you exactly get the following estimate. The left and first term of the right-hand sides are exactly what the conjecture said. And then we get an error term that's big O of this mess here. And the fact that this 12 is somehow related to this 6. And all you have to observe is that as long as Q is big enough turns out to mean bigger than 2 to the 24 times R plus 1, this term here will be little o of 1. In some senses, saying this is a little more precise than just saying it's little o of 1. And what this does is it proves this conjecture for all big enough Q for a fixed R. So I think it's important to point out that it does not prove it for all R for any particular Q. Okay, Q has to be large compared to the moment that you're calculating. So there's no Q for which it tells you something for all R, unfortunately. The conjecture is for all Q and all R. This is for Q big compared to, yeah. Right. So in the last few minutes, I want to tell you a little bit about what goes into this. As I said, this kind of stability theorem, where the range doesn't care what the coefficients are that you're using, is sort of new. There's many results of the previous kind where it decreases with the degree of polynomiality, but there's not really so many where it doesn't. And we don't just do this example. We give a sort of general machine, which also applies to moduli of Riemann surfaces and moduli of graphs and moduli of handle bodies and various other things. But it's not completely without precedent that there is a result where it doesn't depend on Q. There's a theorem of Borel, which if you squint, you can view as a theorem of this flavor. So Borel's theorem says if I have an arithmetic subgroup of the symplectic group and I have a non-trivial irreducible representation, then the cohomology vanishes for I less than G. And in particular, if I have one in SP2G and one in SP2G plus 1, if they both vanish, then indeed they are isomorphic to each other because they're both 0. So from that point of view, you can view the vanishing in a range that depends on G but does not depend on lambda as a very degenerate case of stability. It's stability where both things are actually just 0. So our strategy is to bootstrap somehow from this theorem of Borel. This is, I think, before what we did, the only example of this phenomenon where the range doesn't depend on the degree of polynomiality. So our strategy is the following. We take as the arithmetic groups the images of the Borel representations. So up until now, I said for simplicity, let's take n to be 2g plus 1, odd, so that we're only talking about 1/2 of the cases. For this strategy, it's very important to do all of them. So in particular, you have to decide what you mean by SP n-1 when n-1 is an odd number. It's the so-called odd symplectic groups of Gelfand and Zolovinsky. And it turns out that gamma n is an arithmetic subgroup of that. And it turns out that those also satisfy the conclusion of Borel's theorem, even when n-1 is odd, so it doesn't, strictly speaking, fit into the statement of Borel's theorem. The conclusion is still true. And then, so this sequence of groups, whatever they are, and we know what they are, incidentally, they're roughly speaking, they're not very far from being the so-called level 2 congruent subgroups. They're a bit bigger than that, but roughly speaking that. And then we do the following. We show that if you, let me pause for a second. One lesson that one learns from doing algebraic topology or homotopy theory long enough is that it's in your interest to take homology as late as possible. So it's in your interest to do as many constructions as you can, not with homology, but with, for example, chains, and then take homology when somebody puts a gun to your head. So here, what we show is that the chains, the group homology chains, if you like, on these groups with coefficients in V lambda can be constructed from the chains on all the braid groups with all the V mu's for all smaller braid groups and all smaller mu's than lambda, meaning partitions of smaller numbers, let's say, in a very specific way, which I won't try to explain. And then the strategy is to say that if our homology groups, so the homology of the BMs with coefficients in V mu, didn't have this excellent stability property, then because the way we construct the gamma ends from the BMs is so precise, then neither could Borel's theorem be true. And so Borel's theorem is true, and so necessarily our groups must also have this excellent stability range. So this is a bit of a strange argument. I mean, the more natural thing to do would be to try to build the thing that you want to know by the things that you know something about. Here we do something weird, which is build the groups that we know something about in terms of the ones we don't know anything about, and deduce backwards that the ones that we want to know something about indeed have a good property. So my involvement in this business is entirely these last 5 lines of the slide. But I think it's an excellent and beautiful application of this kind of modular space topological methods to, in this case, arithmetic statistics. So I wanted to tell you about it. Thank you for your attention.
Yeah, thanks for this beautiful talk. Are there questions? Oh, wait, I think we were told to give you the microphone.
So this may not have too much to do with the actual content of the talk, but you mentioned often the Conrey et al. Conjecture, whilst eliding the fact that it was originally a conjecture over number fields, and you're going at the function field version.
I think I didn't elide that. I think I said that, but yes.
Would you expect that these methods would tell us anything new about the original number field case?
No.
Okay, thank you.
I don't think that's a controversial no either, I think.
Other questions? Okay, maybe I also have one question. I mean, I'm wondering, like, is the converse also true? You use topology to deduce something about this initial CFKRS conjecture. What if we, for some other reason, knew the conjecture was true? Could we deduce some homological stability or something?
I think you could try to. The thing is, what you have access to is the sort of alternating, I mean, it's the Lefschetz numbers. And you would have to have some reason to believe that there wasn't some tremendous cancellation going on in those alternating sums, I suppose. But I think in principle you can make arguments of that flavor. I think Jonas Bergström has various papers where he does the point counts by machine and uses that to make conjectures about, for example, the Hodge structure on various cohomologies and moduli spaces. So I think in principle you can, but maybe it's more experimental and less rigorous in that direction.
Okay, thanks. Further comments or questions? Otherwise, before we thank Oscar again, 2 things. I mean, there's a coffee break now until 11 when we resume with Jessica Finson's talk. And also for the postdocs and PhD students, during this coffee break, there's the first talk tutorial for Alice Genet's talk by Rodrigo. And this will take place in S10 upstairs, the lecture room. Okay, then let's thank Oscar again.